11.3, the integral test. In general, it is difficult to find the exact sum of a series. We are able to accomplish this for geometric series, and the series is sum from 1 over open bracket n open n plus 1 close bracket, because in each of those cases we could find a simple formula for the nth partial sum S sub n, but usually it isn't easy to discover such a formula. Therefore, in the next few sections, we develop several tests that enable us to determine whether a series is convergent or divergent without explicitly finding its sum. In some cases, however, our methods will enable us to find good estimates of the sum. Our first test involves improper integrals. We begin by investigating the series whose terms are the reciprocals of the squares of the positive integers. The sum from n equals 1 to infinity of 1 over n squared equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared, and so forth. In sidebar, you have the column n and the column s sub n, which equals the sum from I equals 1 to n of 1 over I squared. There is no simple formula for the sum of s sub n of the first n terms, but the computer-generated table of approximate values given in the margin suggests that the partial sums are approaching a number near 1.64 as n approaches infinity, and so it looks as if the series is convergent. We can confirm this impression with a geometric argument. Figure 1 shows the curve y equals 1 over x squared and rectangles that lie below the curve. The base of each rectangle is an interval of length 1. The height is equal to the value of the function y equals 1 over x squared at the right endpoint of the interval. You have figure 1, where area 1 is 1 over 1 squared, area 2, and so forth. See graph y equals 1 over x squared. So the sum of the areas of the rectangles is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so forth until you get the sum from n equals 1 to infinity of 1 over n squared. If we exclude the first rectangle, the total area of the remaining rectangles is smaller than the area under the curve y equals 1 over x squared for x greater than or equal to 1, which is the value of the integral of 1 to infinity of 1 over x squared dx. In section 7.8, we discovered that this improper integral is convergent and has value 1. So the picture shows that all the partial sums are less than 1 over 1 squared plus the integral from 1 to infinity of 1 over x squared dx equals 2. Thus the partial sums are bounded. We also know that the partial sums are increasing because all the terms are positive. Therefore, the partial sums converge by the monotonic sequence theorem, and so the series is convergent. The sum of the series, the limit of the partial sums, is also less than 2. The sum from n equals 1 to infinity of 1 over n squared equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so forth, is less than 2. The exact sum of the series was found by the Swiss mathematician Leonhard Euler, 1707 to 1783, to be pi squared over 6, but the proof of this fact is quite difficult. See problem 6 and the problem plus the following, chapter 15. Now let us look at the series, the sum from n equals 1 to infinity of 1 over the square root of n equals 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus 1 over the square root of 5, and so forth. Sidebar, see table n and s sub n, column n and column s sub n equals the sum from I equals 1 to infinity of 1 over the square root of I. Back to the text. The table of values of S sub n suggests that the partial sums aren't approaching a finite number, so we suspect that the given series may be divergent. Again, we use a picture for confirmation. Figure 2 shows the curve y equals 1 over the square root of x, but this time we use rectangles whose tops lie above the curve. Y equals 1 over the square root of x. And you have an area 1 over 1, 1 over the square root of 1, and area 1 over the square root of 2, and area 1 over the square root of 3, and area 1 over the square root of 4. The base of each rectangle is an interval of length 1. The height is equal to the value of the function y equals 1 over the square root of x at the left endpoint of the interval. So the sum of the areas of all the rectangles is 1 over the square root of 1 plus 1 over the square root of 2, all the way until you get to the sum from n equals 1 to infinity of 1 over the square root of n. This total area is greater than the area under the curve y equals 1 over the square root of x for x greater than or equal to 1, which is equal to the integral from 1 to infinity of open 1 over the square root of x close dx. But we know from section 7.8 that this improper integral is divergent. In other words, the area under the curve is infinite, so the sum of the series must be infinite. That is, the series is divergent. The same sort of geometric reasoning that we used for these two series can be used to prove the following test. The proof is given at the end of this section. The integral test: suppose f is a continuous positive decreasing function on open bracket 1 to infinity close, and let a sub n equals f of n, then the series the sum from n equals 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. In other words, number one, if the integral from 1 to infinity of f of x dx is convergent, then the sum from n equals 1 to infinity of a sub n is convergent. Number two, if the integral from 1 to infinity of f of x dx is divergent, then the sum from n equals 1 to infinity of a sub n is divergent. Note, when we use the integral test, it is not necessary to start the series or the integral at n equals 1. For instance, in testing the series, the sum from n equals 4 to infinity of 1 over open n minus 3 close squared, we use the integral of from 4 to infinity of 1 over open x minus 3 close squared dx. Also, it's not necessary that f be always decreasing. What is important is that f be ultimately decreasing. That is, decreasing for x larger than some number big N. Then the sum from n equals big N to infinity of a sub n is convergent, so the sum from n equals 1 to infinity of a sub n is convergent by note 4 in section 11.2.